Okay, in the beginning of this course, what we did, we started talking about inductors and capacitors, right? And inductors, and one of the things that we assumed at the beginning is that there is no significant flux linkage, magnetic flux linkage between these things. When we were writing KVL, for example, we assumed that there is no magnetic flux going through the loop and all those things. But that's not generally true, right? And the magnetic flux linkage, basically, when you have two elements that are magnetically coupled to each other, can be an important and useful part of the circuit design and also kind of like understanding the system, and you can do a lot of useful things. And one manifestation, one very significant manifestation of this is transformers. Now, I'm sure most of you have seen transformers. You may not have realized that you've seen transformers. If you look at the power lines, for example, when you do the local distribution, there's this little cylindrical gray thing, blue-grayish thing that looks like underneath, and then that's where basically the down conversion happens. So it's used in power systems a lot. Transformers are used also kind of like they're used in impedance matching for AC circuits at certain points. They're also used at high frequency circuits, RF and microwave circuits, for impedance matching and impedance control. They're also used for isolation from time to time, because you can have two parts of the circuit, the primary and secondary, that are completely isolated other than the magnetic connection. So there are lots of applications and uses for them. So what we'll do today, we're going to do a preliminary introduction to how we think about transformers and how we model them as a circuit element. And when in the process of doing that, we rely a lot on the two-port models and two-port modeling of the circuits that we've discussed. So one of the things, so let's start thinking about transformers, right? It's a magnetic element. So transformers. And the first thing actually you think about is an inductor. Let's think about an inductor, review our inductors, right? So what was an inductor? If you remember, what was our definition of an inductor? So let's say I have a voltage and a current and an inductor. How did we define an inductor? What was the definition of an inductor, right? We had a definition of resistor. In general, the most general definition of a resistor was an element whose current is a function of its voltage, or its voltage is a function of its current. And then we had a capacitor whose charge was a function of its voltage. And an inductor was an element whose magnetic flux, or magnetic flux linkage, is a function of its current, right? So in general, an inductor is an element whose magnetic flux is a function of its current. But a linear inductor, an LTI inductor more precisely, has its magnetic flux, or magnetic flux linkage, linearly proportional to the current. And that proportionality constant is called the inductance. We've seen this before, and this is the current. So, and we know that if you have the magnetic flux as phi by Faraday's law, we know that the voltage across this device is the derivative of the magnetic flux, right? d phi dt. And if you plug that in, you get L di dt. And so that's LPI in our notation, right? Using the Heaviside operator. So this was a definition of an LTI inductor, right? So this is a single inductor. This is the way it behaves. So now, and of course, if you want to calculate the current as a function of voltage, you can of course do the opposite of this thing to integrate it. So it would be 1 over L integral from negative infinity to t of v of t dt, which you can also write as 1 over L p v in our notation. Right? So these are things that we've already done. These are things that we've already analyzed. So that's fine. Now, how is this really done? I mean, if you think about an inductor, there are different ways to make it. But one of them is that if you have some sort of a magnetic core, you don't have to have a magnetic core. You can have an air core or any kind of other material. But let's say you have a magnetic core, and then what you do, let's say you have a set of a winding on this. That's coming in. So this is a current I and the voltage V, and this is wound a certain way. So this induces a magnetic flux, right? Magnetic flux linkage, if you will. So which way would it go? You can see that it's going this way, the current. It's going in this direction. So you can basically think about it using right-hand rule. there's a magnetic flux linkage that's in this direction. So that, right? Because you can think about this, you can actually wind it the other way around. You can wind it in the other orientation, and then it would induce a magnetic flux that goes in the other direction. And we'll see in inductors this matters, which way they're wound with respect to each other, the direction of winding. So in transformers. So this is an inductor. This is how, and this can be a magnetic core or something that produces, usually this is, for example, can be an pure iron core or something like that, that produces a strong magnetic coupling, a ferromagnetic core that produces a strong magnetic coupling to something else. Now, so to make a transformer, you use a second winding, right? You have a second winding in the case of a transformer. And this winding can be done in two different directions. So let's say, first, I'm going to do it this way. And let's say, so now let's say if there's a current going in this direction into the transformer, what way would it induce magnetic flux? Think about it, right? It's going to produce a magnetic flux that would be coupled this way, or this way, you can think about it. Which is, in this case, now you can see that they are actually both produce this magnetic flux in the same direction, right? They're both producing a magnetic flux that in this picture goes clockwise. So they're coupled basically directly, right? Same flux link, they have the same flux linkage. So now in general, you can think of, so this direction matters because I can actually draw a different picture, and I will show you in a second, that will have the opposite flux linkage. Now, if you have this kind of flux linkage, the symbol we have, and of course you have two currents here, so let's call this I1 and V1, and let's call this current I2 and V2. Now, in this picture, the symbol that we use for this looks like this, but we have to kind of somehow identify the fact that these two are now have the same flux linkage, same orientation for flux linkage. And the way we do it is that by putting a dot either up here or here. And if these two dots are in the same place, they would be considered to have the same flux linkage. So this is I2, this is I1. And so that's the kind of like very general picture that we use. Now, what if the flux linkage was in the opposite direction? What, in that case, I mean, I'm going to redraw this picture with the opposite flux linkage just in case. But I'm not going to make it as clean possibly. And let's say, so now I got to go from underneath and come back up. Right? So now if you look at it carefully, the red side still has the same flux linkage as before. The direction is in this direction, right? But this guy, if there's a current coming in this direction, what it does, it produces something, the flux direction that goes in, flux linkage that goes in the opposite direction. So the way we draw this picture, and to keep it consistent, is that we draw a similar symbol, and we put a dot here, and the other dot is there. So it's in the opposite orientation, meaning that they are out of kind of like they have opposite linkage. Now, one of the things to keep in mind is that when you do this, generally, as far as transformers are concerned, the convention is that the currents always go into the dotted, the direction of the conventional direction of the current, which may not be the actual exact one at any point in time. I2 and I1 can be positive or negative, but the convention is that the current goes into the dotted terminal and the voltage is referenced to the dotted terminal. So the dotted terminal becomes a positive reference for the voltage. Now, that doesn't mean that that voltage is always positive, right? It can be positive or negative, but this is basically what it will look like. So how do we model this? So the total flux link, now, so what do we do about one of these things? How do we model it mathematically? So remember, for a single inductor, we had the flux. linkage associated with it that was induced only by its own current. But now you can see that the flux that's linked to this first inductor, the red inductor, right, is induced really by two parts. One is its own current, right? Its own current has a role, so we call it L11 I1. And then we have the current of the other inductor will induce some flux, right, in this loop. So let's call that L12 in general I2. And similarly, for the other one, by symmetry, you can actually write something like this. So these are the two flux linkages. So this is the total flux through the inductor 1, which determines its voltage, and the total flux through the inductor 2 that also determines its voltage. And you can also write it in a more compact form, phi1 and phi2. In the matrix form, obviously, this is designed to be a matrix format. I1 and I2. So this is the I1 and I2. Now, one of the things that I'm going to state without proof at this point, and we'll prove it later. So we will prove this later, but we'll now use it a lot because that proof is a little bit longer, so it would distract us from the main conversation. And we'll do it, but we will prove it, is that in an actual inductor, in an actual transformer, L1, 2 equals L2, 1. And we call this thing M, the mutual inductance. In other words, it's reciprocal. I haven't proven this. We haven't proven this. I'm just stating it now. But it's true. And I'll show you why later. But let's start with that. So if you write it this way, then it simplifies and it becomes a little bit simpler. And in that case, we don't really don't need the L11 and L12. So we write a simpler notation, L1, M, M, and M2, L2, sorry. L2 times I1 and I2 gives you phi1 and phi2, the flux linkages associated with this. So there are really three parameters. And one way to think about it is that L1 is the self-inductance of the primary, or the first terminal. L2 is the self-inductance of the second terminal. And M is the mutual inductance. It's a measure of how strongly they're coupled to each other. And you can see, if, for example, M were 0, if you set M to 0, then you will see that the flux linkage only comes from its own, for each one of these in primary and secondary, will come from its own current, which basically means that the other terminal's current does not matter. And they're not coupled. They're two independent inductors that are not coupled to each other. So that kind of makes sense. So, but these are flux linkages. We don't usually deal with a lot with flux linkages in circuits, right? We usually work with voltages. So how do we go from flux linkages to voltages? Well, we know this relationship. The voltage for each one of the terminals related to the flux derivative of the flux linkage. So what you can say, okay, so V1 and V2 are going to be the derivatives of these things. So it can be L1 di1 dt plus M di2 dt. And this one is M di1 dt plus L2 di2 dt. So now this is a relationship between voltages and current. And if you want to write it in our more compact notation, you can write V1, V2 as a matrix. You can write it two different ways. You can write it as L1, M, M, L2, di1, dt, di2, dt. Or you could write it as L1, M, M, L2, Pi1, Pi2, or you could even absorb the p's into the matrix if you really wanted to. So you can say L1p, MP, MP, L2p operating on I1 and I2. You could think about it that way if you prefer. And of course, if you wanted to write it in Laplace or Fourier, you can write it as L1s. So alternatively, in Laplace domain, it would be L1, M1, MS, MS, L2s, I1, and I2. And if you wanted to go to Fourier domain, then it would be basically Lj omega, L1j omega, Mj omega, mj omega. And we've talked about these different domains before, so I'm just writing it quickly. So you can do the same thing that you did with all of the other elements, either in operator domain, or Laplace domain, or Fourier domain. So nothing magical right now so far. And it's a pretty straightforward thing to deal with. So it allows you to deal with actual analysis of these things. So we can do a couple examples. Let's do a couple of simple examples. So here. So the first example is a simple one. So let's see. So let's say you have a current source, Ig of t, that's applied to the primary of a transformer. And the secondary of the transformer is open, let's say. Right? And let's say L1 is 2 henries, L2 is 4 henries, and the mutual is 3 henries. And the dots are the opposite. So let's say they have opposite linkages. And let's say Ig of t is 4e to the negative 2t amps. Okay? And the question is, what is the output? Like u of t. So how would you calculate the output? Output meaning this voltage. Let's say defining this voltage, v of t, as the output. We want to find what is that output. What do you think it is going to be? What do you expect it to be? I mean, any sense of what, or expectation of what it would be? Any guesses? This is an LTI element, right? So you're hitting it with some sort of a natural frequency exponential. You're going to get that frequency. I don't see any other resonances here, so I suspect that it would not be anything else. It would just some scaled version of the e to the negative 2t. That's what we expect to see. So if you see a whole bunch of other new things, then you've probably done something wrong, right? Okay, so how do we do that? Well, we write those equations, right? We know V1, the voltage at the first terminal, is L1 p I1 plus M p I2. But I2 is what? What is I2? 0, because it's open, right? So this is 0. So this becomes, what does it become? And L1 is 2, so this becomes 2 p I1. So that's the relationship between V1 and I1. Okay. And now what about V2, the second equation? V2, but we have to remember, the way we've defined the voltage of this terminal is a negative of the output voltage, because it needs to be referenced with the negative. So I've said negative V2 is equal to, or negative V, let's say, so which is V2, is going to be what? MPI1 plus LPI2. Again, I2 is 0. So you get 3, M is 3, 3p times I1. But now I1, look at it, the current that's going into the terminal, what's the polarity of that? It's negative, right? Negative Ig. So this is negative Ig here. So we can calculate from this equation by itself what is the output V2 in terms of, so output V. So V is going to be negative 3p negative Ig, right? And what is that going to be? So it's just the derivative of what Ig is, times 3, right? So you get 24. If you differentiate this, what do you get? You get negative 2, right? So let's get all the coefficients. So you get 3 times the derivative of that guy, which is, so it's times 4 times the derivative of that, which is negative 2 e to the negative 2t u of t. So you will have whatever, like 12 times negative 24. du of t, yes, you do, if you take it into account. So that's why I kind of like was hesitant to put this here from the beginning first or not. So if you put the u of t, then you have to differentiate, so that there's an impulse generated there. So there's an impulse, could be an impulse generated there. But again, if you just have this exponential like that, that's right. But I mean, then there could be a secondary term, possible impulses, other things. Okay, so that's one example. Now the other question is, so let's do another example, a little bit more interesting, or a little bit more, I guess, involved. So let's say you have a Vg of t, right, applied to a transformer. And now, in general, by the way, these two bases of the two lower terminals of the transformer do not need to be connected in general. But in this example, let's assume that they are connected. So they are connected both to ground. And then let's say it's connected to a resistor, a 5 ohm resistor. And let's call this voltage V of t. This is what we are trying to determine. Let's say these two transformers now have the same flux linkage, same values, 3 henries, 2 henries, and no, actually not same value, 5 henries here, so I2 and I1. And you look at these three, and then you say, okay, well, okay, let's find out what's the V in terms of Vg. And Vg, let's say this time it's, so let's say Vg of t is 20 u of t. So it's just a step. Okay? So if it's the step that's applied directly to it, what do you get? So how do we solve this problem? Now we write these equations that we have, but now we can write it in the S domain, or P domain, or whatever you want to write, right? So what are the general equations describing this thing? We have a V1 of S, right, which is L1 S I1 of S, plus M S I2 of S. And then for V2 of S, we have M S I1 of S plus L2 S I2 of S. Right? So these are the two sets of equations we have. Now, how about Vg? We know what the Vg in the S domain, so Vg of S is going to be what? What is Vg of S? What is the, if you want to kind of think about it, Laplace transform or the operator that represents this, generates this off of an impulse? What is it? 20 over S, right? Because if you want to generate a step off of an impulse, you need to integrate it. It's 1 over P. Right? Okay, so that's one thing we know. And then the other thing is, okay, so what do we do with these things? So there are a couple other things. What else do we know? What other relationship we have? We haven't used the fact that we have a resistor, right, at the output. That resistor produces what? A relationship between what and what? The I2 of S and the voltage, right? That relationship is what? So it's Ohm's law, right? So it says R times I2 of S is going to be what? V of S or V2 of S? Yes? No? There's a little subtlety there. Look at the direction of the current. So it would be negative V2 of S, right? Because it's the current that's going in this direction. So you need to keep that in mind. But other than that, so basically that makes it numerical. So we can actually make this numerical, right? So first thing is that we know if we plug this into this equation and write it numeric, so we can take this V2 of S and plug it here. So we get negative 5 I2 is going to be M, which is 3 S I1 plus L2, which is 5 S I2. So this produces a relationship between I1 and I2. So you can actually solve for one of them in terms of the other. So you can actually solve for, let's say, I2 in terms of I1. So I2, if you move this to the other side and factor 5, would be 3S over 5 S plus 1 I1, if I'm not mistaken. Yes. Okay. Now the other thing that you know is that you know Vg is V1. So this is Vg. So you know Vg of S. So it's basically algebra really here. L1S I1 plus M. So I'm using this equation, this first equation. I'm just replacing V1 with Vg. And I get MS I2. Now, since we've solved for I1 in terms of I2, you can plug this I2 into this equation. And we'll make it numerical. So it becomes 2S I1 plus 3S now times I2, which is, again, this thing. So it becomes 9S squared over 5S plus 1 I1. And if you just add them up, I think what you get, so let me just double check. Yeah, the only thing is that here I missed the minus sign because I have to move this here to the other side, right? So there's a minus sign in front of this thing. So this becomes negative minus that. So that's one little error there. Okay, so then you have 2s minus this. So you have 2s minus 9s squared over 5s plus 1 times I1. And we can simplify this. This is algebra, right? So you can say this becomes 10s squared plus 10s minus 9s squared divided by 5s plus 1. So it becomes times I1, which is, so this becomes 9 and 10 cancel, so this cancels the 10. So you get s times s plus 10 divided by 5 over s plus 1 times I1. So this is a relationship that defines I1 really in terms of Vg, because Vg, we know what it is. So now what we are trying to find is V2 in terms of I1. So what's the relationship? So we know V2, which is what we are trying to find really. So V2, so we are going to use this equation. V2 is going to be negative R, which is 5, I2. Now, an I2 can be written in terms of I1, which is this expression. So it's basic algebra really. 15s over, so I'm using this one, and the 5 and the 5 in the denominator actually cancel, so I guess 3s over s plus 1 times I1. And now I1 can be written in terms of Vg. So an I1, this is 3s divided by s plus 1 times 5s plus 1 divided by s times s plus 10 times Vg. So this, what cancels what? Okay. So this cancels that, this cancels that. So you're left with 15 over s plus 10 Vg. And Vg itself was 20 over s, right? So 20 times 15 is 300, but it's better to keep it in the factored forms, right? So it's basically, this is 2 to the 2 times, okay, times 3 times 5 to the 2 divided by, so and then what you have, so this is the factor up front, and then you have 1 over s and s plus 10. And you need to do a, basically, what do you need to do? We need to do a partial fraction expansion, right? So you can do a partial fraction expansion of this thing, which is a pretty straightforward thing to do. So you can say, okay, there are coefficients for s, and then there's a coefficient for s plus 10. So for s, set s to 0, this becomes what? 1/10. So 1/10 of 300 is 30. And then set s to negative 10. So it becomes 1 over negative 10. So this becomes minus 30 over that. Okay? So this is V2 of S, or V of S. So what is the answer? What is the thing that we are looking for? V of t, right? What is it? What do you get from the first one? What is this? 30 u of t. And then what do you get from the second one? 30 e to the negative 10t u of t, which you can simply write as 1 minus e to the negative 10t u of t. Right? So that's the response. So if you put a step into the transformer, you see, if you look at it in time domain, the picture really is that you hit it with a step, but it takes some time to get to the right value of the voltage at the output. So it has a time constant. Why does it have a time constant? Why doesn't it respond immediately? Say again? The resistor and the inductor, right? Together they form a time constant. There's some energy storage element, right? But what is the order of this circuit? Since these inductors are coupled, the way they are coupled and all those things, the order actually is 1. This is a first order circuit because of the way they are connected and coupled. So that's an interesting thing to keep in mind. Okay, so that's one of the parts of the discussion at the transformer. So this is 2 examples to just give you a sense of what happens. But there are ways to look at transformers that are quite helpful. There are these models. They're simplified models of the transformer and its behavior that can be quite useful in the analysis and looking at the transformer and understanding. So now, in general, we know about a transformer like this. So let's say you have a transformer. And then we know that there's always a 2-port model. We've talked about 2-port models before. And so there's a 2-port. And then you have, of course, for a 2-port, you have a V1 and I1. And you have a V2 and I2. So this is a 2-port. Now, what is a constraint for 2 ports? Just to refresh everyone's memory. What makes it 2-port? Not every 4-terminal device is a 2-port. Right? There's something that needs to be true for it to be a 2-port. What is that? Do you remember? Yes? The currents on each side have to be. Correct. So this current also has to be I1. And this current has to be I2, exactly. And this is a significant constraint. So not every 4-terminal thing is a 2-port. But this holds here, right? The way it's connected. So this really does qualify as a 2-port element. So now you have this element. And then you have, and then we can think about it as having an L1 and an L2, and this is the way we show it. M, the mutual coupling. So the 3 parameters are shown like this. Let's say the dots are here, and they're coupled to each other. So we know that this is represented by what? We know that V1, V2 is represented by, you can write as L1P, MP, MP, L2P times I1 and I2. Now, which kind of, we saw that there were different words to characterize the 2-port, right? There are many different kind of sets of parameters. So which sets of parameters do you think would be most suitable to characterize something like this? I mean, in its form, what does it represent? What kind of parameters? It's a z parameters, right? So basically you can think about, because z parameters are basically a relationship that say v1 and v2 is equal to some z11, z12, z21, and z22 times I1 and I2. And as such, it's very clear to see that z11 is L1P and z12 equals z21. So we basically, by what we stated, we haven't proven yet, the reciprocity of this thing is MP and z22 is L2P. So these are the 3 set parameters that you have there for the z parameter. Now what we know, if you know these 3 parameters of a z 2-port, there's an equivalent circuit, right? What is the equivalent circuit? The equivalent circuit looks like this. So there are different ways to write equivalent circuit, but one way to model it is something, well, not resistor, an inductor actually. An inductor here. So this inductor is what? This is L1P, this is L2P, And this is MV2, and this is MPV2 and MPV1. So you can see that this equivalent circuit captures what the behavior of the, not V1, sorry, I1 and I2. I2, because they're in terms of I's, right, I1. So you can see that you can think about a transformer as the two inductors, the primary inductor and secondary inductor, with a dependent voltage source that's dependent on the current of the other terminal, or the other port, more accurately. Right? So you can see that there's a voltage induced at in the primary due to the current of the secondary, and there's a voltage induced in the secondary due to the current in the primary. So that's what the transformer does. It captures a part of these things are coupled to each other. And because of the reciprocity, which we haven't proven yet, of the transformer, this coupling is both related to M. Now, what if this was inverted? What if the dots were in the opposite direction? So let's say, I'm going to make a little small one here because it's really not that important, but just it's good to know about this. So the same deal. The only difference is that the dots are now in the opposite direction. So this is M, L1, L2. What is the two-port model for that? Or what is the representation, the representation of in this format? If you think about it, the representation for this format is going to be the same thing except for a minus sign. So it becomes L1P, it becomes negative MP, because now they are coupled in the opposite direction, right? L2P. And you can use this to basically make current sources, voltage sources that are in the opposite direction. So they would be pointing in the other direction. So that's one way to generally think about it. But there's a particularly useful kind of like equivalent model for this. If you remember from the Z, when we were talking about Z matrix, right, and two ports, one of the things that we said is that if you have a two port that's represented by a Z parameters like this, I1 and I2, and then, so I1 and I2, and then this is the two port that was represented by it. But if these two were connected, these two were shared, one of the things you could do, you could show this as a T model, as a T representation. And if it was reciprocal, so it was connected plus reciprocal, meaning Z12 equals Z21, then you could represent this thing as a T model, what we call a T or a Y representation. So it's just like a T. If you draw it this way, it becomes a Y. It's the same thing. And what were the values of these three? Does anyone remember? This one is that Z12 equals Z21. Right? Which makes sense. That's the kind of like the connection between the two ports. That kind of intuitively makes sense. And from that, you can actually get this thing pretty straightforward. Because when you look into this one, you should see Z11, right? When the other port is open. So if you leave this open and you look into this thing, whatever this is plus this should give you Z11. So what should it be? It should be Z11 minus Z12, right? And similarly from this side, if you look at it, you should see Z22 if the other side is open. So this is Z22 minus Z12. So this is a simple way to remember this. I mean, you don't need to really remember it. I mean, if you know that the middle one is going to be the off-diagonal element, then the other two have to be, this has to be Z11 when the other side is open, this has to be Z22 when it's the other. So now if you apply this simple model to a transformer, so let's say you have a transformer whose other two terminals are connected. And this is, by the way, not necessarily the case, this connection. Actually, one of the advantages, one of the uses of transformers is to isolate one port from the other and have these be on different grounds, for example, connected to completely different things. But if it is connected this way, and we'll see how that's modeled at the very end of this discussion, if it's modeled that way, and this is L1, and this is L2, and this is M, and let's say they have the same linkage, flux linkage coupling, what do you get? What is the equivalent circuit for this? So you see that this is simply can be modeled if that connection exists, and of course if it's reciprocal, which we've said it is, but we haven't proven yet, then what are these values? So it's pretty straightforward if you think about it. What are those three inductors? What is the middle one? M. It's an inductor with a value of M. And then what is this one then? Look at this. L1 minus M, and this one is L2 minus M. So this is a pretty useful equivalent circuit if you think about it. Because it takes a transformer, not any transformer. If the negative terminals of the transformers are shared, you can always reduce it to this. It's a pretty simple model. So if you don't want to really worry about the transformer and the coupling and things of that sort, and if you have that particular connection, this will happen. Now, what if the polarities are the opposite? So let's say the flux linkage is reversed. So you have this, but the flux linkage is the other way. Well, look at this. Right? So what is the equivalent circuit now? So this is going to be negative M. So it's going to be an inductance with a negative value. And you can say, well, what do you mean inductance with a negative value? And this is going to be L1 plus M and L2 plus M. It's okay. It's a circuit abstraction. Because if you think about it, if you look at from either one of those terminals, you will never see that negative one. Because it's added to a positive one of the same value. But from a circuit representation perspective, you can actually deal with it as a negative value. So if they're coupled the other way around, this becomes negative, and then these become positive. But again, it's a useful thing. Now, we also know from the two-port analysis and two-port discussion that you can convert a Z matrix to a Y matrix. How do you do this? Now, by the way, this Z matrix and this Y matrix have nothing to do with the Z matrix Y matrix and Z matrix that are generated in the nodal analysis or mesh analysis. And in fact, these guys, this Z matrix and this Y matrix for two ports, are inverses of each other. So what you do for this particular, for the two ports, Y is Z inverse. So you can calculate the Y matrix, and if you take a Y, then that leads to another equivalent model, a little bit less useful. But I'm just going to draw it just so that you know what we call a pi model, because it looks like a Greek pi, right? And the values of these things, if you do this matrix inversion, this is what we call LA prime, LB prime, and LM. And LA prime is the determinant of Z over L1 minus M, L2A, yes. L2 minus M, and LB prime is determinant of Z, or it comes out of matrix inversion directly, M, and LM is the determinant of Z over M. So this is a useful thing to know. I don't expect you to remember this. This is, I think, a simple enough thing to know and remember. But know that this basically, you generate this alpha by inverting this 2 by 2 matrix. If you invert it parametrically, those are the parameters you will get. So yeah, what's the point, what's the value, et cetera, et cetera. It's good to know that there are these kind of equivalent circuits. Okay, so that's a little bit of a basics. So then let's go back to this discussion about, let's talk about this reciprocity. And it goes back to the energy discussion. What is the energy stored in the in a transformer, or in general, a coupled device? So we're talking about energy considerations. Energy stored in a transformer. So think about a two-port in general. If you have a two-port, what is the, we talked about one ports, right? And we said, what is the power delivered to a one port? This was, I think, the first lecture, something like that, right? What's the power delivered to a one port? Like if you have a two-terminal device, like a resistor or an inductor or a capacitor or something. It's the voltage times the current, right? Instantaneous power. You remember? It's V of t times I of t. It's P of t. So for a one port, the power is the voltage times the current. But now if you have a two port, the power that goes into the two port is the sum of the powers that goes into each one of the ports, right? So the total power is going to be V1 of t times I of t, I1 of t, plus V2 of t times I2 of t. So this is the power. And there's one more thing we know about an inductor, right? There are a couple other things we know about it. But one particular thing that's important to know about an inductor is the fact that, do you think inductor is a passive device or an active device? From what, sorry, a transformer, not inductor, a transformer. Is it a passive or active? Does it have an energy source inside? No. So the total energy that it absorbs over time cannot exceed the total energy that it puts out cannot exceed the total energy that has gone into it, right? So it's a passive device. And this is one of the things that will help us do that in the derivation that we are going to do. And essentially the proof and the derivation and the proof of the fact that it is reciprocal. So the other thing that we know, if this is an actual transformer, so then you have the mutuals, L1, L2, and let's say they're in phase. So we know that there's this relationship between the voltages and currents, right? So in general, you can write this relationship as, we know V1 is, or V1 of t, is going to be L1 P I1 plus M. Okay, and let's not write this as M for now. Let's write this, let's assume that in general, these are like L11 and L12. So we go back to our original notation, because we want to show what we are trying to prove is that L12 is equal to L11. So we have an L1, L21, I plus I1 plus L22 P I2, right? So this is the general relationship, right? And we want to, at the end of this discussion, we want to come out with a conclusion that L12 and L21 are equal. That would prove that reciprocity. So that's what the end result of this kind of like writing on, filling up this whiteboard would be. Possibly another whiteboard too. But okay. So let's look at this. So this total power, if you plug these things into here, what do you get? If you plug these two terms into here. So you get L11. So let's write these. And you have to be careful because you have the derivative. So you have an L11 from the first term, I1 P I1. And the reason I'm writing this is that because this is times this, the derivative of that. So I have to be careful which side of P I'm putting it on. Plus, then you get this one, where you get L12 I1 P I2, right? From this first term. And then from the second term, we plug this one in. So we'll get plus, then you get L22, I'm starting with this, I2 P I2 plus this term, which is L21 I2 P I1. Right, so it would produce 4 terms. Now, couple of things. So this kind of terms, like XPX, is there a simple way, another way to write this? X times x prime, or x times its derivative, right? Do you agree that this is P of x squared over 2? Or y squared or whatever, some function, right? If x bothers you, it shouldn't, but let's make it y. Right? Isn't the derivative of that y times y prime? And this isn't this y times y prime? So this thing itself is what? That first term is L1 P I1 squared over 2. And similarly, this term is did I say L1? Okay, L22. L11 and L22 I can keep as L1. I mean, it just doesn't matter. We can keep it. So that's not the concern. So I'm just going to drop one of the 2's or 1's. or it doesn't matter, let's keep it. I2 2 over 2, right? So this is these two terms. Okay, we can write them that way. Now, how about the other two terms? Now, one thing is that in general, you notice one thing. We notice that you have an I1 pi2 and I2 pi1. These terms arise from what? If you have the derivative of u and v, u times v is u v prime plus vu prime, right? So the derivative of a product, obviously. So they arise from that, but they don't have the same coefficient, it appears. So what do? Well, we say, okay, whatever these coefficients are, they're different. So L1, 2, and L2, 1 are some different amounts. But I can write both of them. So there's some difference between them. Let's call that delta m. So I can write this as m plus delta m. And I will call this as m minus delta m. So the difference of these two is 2 delta m, or delta m over 2. Let's make it simple. So if the difference is delta m over 2. So delta m, by definition, so what we are saying is that delta m is L12 minus L21, right? So whatever the difference is m plus that difference and m minus that difference. We define that the average of them as m. So m is also defined as L12 plus L21 divided by 2. So we define m as their average, and delta m is their difference. So you can always write it in this form, right? Any two functions, you can write it as their average plus half of their difference, or minus half of their difference, depending on which one you're trying to get. So if you do it this way, then it leaves two sets of terms. So the first set of term is the one that has m. So we can keep those two together. So you get m part, and then you get I1 pi2 plus I2 pi1. So that's the common part, plus delta m over 2 I1 pi2 minus I2 pi1. So this is pretty straightforward, right? This is, you know what this is. What is that? That's p of I1 times I2. It's a derivative of this product of I1 and I2, right? Do you agree? So this is p I1 I2. So that's what this is. How about this? When do you get the difference of two things? When do you get that? What kind of mathematical relationship between two functions produces that something like of that form? It may have some other things in it too, but I1 over I2, yes, right. The division, right? Correct. Yes, exactly. Right? So this is really p of I1 or I2 over I1 times I1 squared. Do we agree? So we have those two terms. So now the good thing is that now all of them are written as some derivative of something, right? So now you can actually write this in an aggregate form, except for the last one. So you can write this as p of L11 I1 squared over 2 plus m I1 I2 plus L22 this should be I1 L22 I2 squared over 2, right? So this is the derivative of all these three. So it's this term plus these two terms. This last term, I'll keep it separate, so I will write it as delta m over 2 I1 squared derivative of I2 over I1. Okay? So you have these three terms in the beginning, and then you have that delta term. Now, the total energy delivered to this thing is, of course, is what? The total energy delivered, this is the power, right? The total energy delivered up to time t is what? What's the relationship between, so this is the energy delivered. We've done this before. Energy delivered is going to be the integral of the power, right? So if we want to calculate what's the total energy delivered, which is going to be the integral of the power, is going to be the integral of this thing, which is basically simply L11 I1 squared over 2 plus I1 I2 plus L22 over L22 times I2 squared over 2. So that's the total energy due to this first three terms. It's just like a different integral of the derivative. Now here you have to integrate it, right? So this becomes delta m over 2 integral from negative infinity to t, or negative infinity to whatever, yeah, to t, that's w of t, I1 square of t, the derivative of I2 over I1 dt. Prime. Okay, this is I of t prime, etc., etc. So we'll get to it. This is the proof, right? So we're going to get to the proof. So this is the total energy delivered at any point in time t. So now let's imagine that you have a function I1. So this should be true for any arbitrary value of I, right? Any functions of I1. This is a general expression for I1 and I2. So we'll pick an I1. So let's say I1 of t has the following form. It is non-zero for a period of time in the middle, and it's 0 before and after. It has some shape. Right? You can pick any shape you want, but in general this is true, right? And now we make I2, since I1 and I2 can be independently controlled, and this should be valid for any value of them, we'll pick that as negative t I1 of t. So now if you integrate this from negative infinity to positive infinity, so at positive infinity, we want to see what we have. So at positive infinity, what is this value? It's the first term in the energy. 0, right? Because this is going to 0. How about this one? That's 0, 2. How about this one? That's 0, right? So all three of this first term will be 0. The only thing that becomes non-zero is this term. So at that point, so let's say, what is p of I2 over I1 for this definition? Well, I2 over I1 is negative t. It's p of negative t. So it's negative 1 for this particular function. So what you get, that becomes negative 1. So it becomes delta m over 2 integral of negative infinity to positive infinity of I1 of t squared with a minus sign, right? Because of that negative sign, dt. So whatever this is, we just need to know one thing about it. What is its sign? It's positive, right? The integral of this function is positive, the way we've defined it. So this is a positive. But remember, this is a passive component. Bless you. This is a passive element. So the total energy delivered from negative infinity to positive infinity to it has to be positive, right? Because it can't, if it's negative, it means that it has produced energy, net energy, in the course of history, right? So therefore, it means that in this case, it means that delta m needs to be smaller than or equal to 0. Agree? So now I'll repeat this process with just one modification. You say everything is the same. Now this time I2 is t I1 of t instead of negative t I1 of t. So what would change? Again, the first three terms remain 0. P of I1 over, or I2 over I1, which was now becomes P of t, becomes plus 1. This integral, and what this becomes, so w of plus infinity becomes plus delta m over 2 integral from negative infinity to positive infinity of I1 square of t prime dt prime. And this is a positive quantity, so this needs to be positive. So delta m has to be greater than or equal 0 for these two sets of definitions. And of course, these two combined tell you what? If both of them are true, right, that means that delta m has to be 0, which means that it's reciprocal, which means that basically means that because delta m was the difference between L12 and L21. So that means that L12 is equal to L21 is equal to L12, which is we call m. So this is the proof. If you care about the proof, if you don't, that's fine. It exists. The existence of a proof. The proof of existence of a proof. It's not the proof itself. Anyway, okay. So, what else can we say about the inductors? Now, this calculation that we did is actually quite useful more than the proof. I think this is probably a more useful part of it than the proof, which is that, so now that we know that the energy, delta m is 0, we know that the total energy delivered to the inductor is simply what? Is L1 I1 squared plus m I1 I2 plus L2 I2 squared over 2. So now if you look at this, this kind of makes sense, right? So it says that there are really energy stored 3 different ways. One, the first term is the energy of an inductor. If you had a single inductor with a value of L1, right? What is the energy stored in it? Is it 1/2 L I squared? And also same thing for the secondary inductor. That's the energy in the secondary inductor. And then there's some energy, in principle, stored in the mutual part of this. So there's extra energy stored in the mutual coupling between these guys. Now, one of the things you could do, you could write this as, so you can factor L1 and write this as, so you can basically just look at twice the value of this. So if I write 2w of t, right, we get L I1 squared plus 2m I1 I2 plus L2 I2 squared. And we can manipulate this a little bit algebraically to arrive at a useful relationship, an interesting constraint. So that comes out of the energy consideration. So if you write this as, if you factor L1, you can write as I1 plus m over L1 I2 squared, right? What is this term? And there's another term, which we'll write. What is this term? This term is L1 I1 squared. So if this is that term, then you get 2m I1 I2. So you get the first 2 terms, right? But its third term is different from this. Its first third term is m squared over L1 I2 squared. Now, to get it to this term, you need to subtract this and add that. So you need to add this and subtract this, right? So do you agree that this is now correct? This is an equality? I just subtracted this difference that came out of this full perfect square, and I added whatever I needed, which is this one. Can I erase this? Is it okay? All right. So do you agree that 2w is this? So now, this should be valid for any values of I1 and I2, right? So what if I pick my I1? So assume, or let's say, assume I1 is negative m over L1 I2. Can be any values, right? This should be valid for any value. So if we pick that value, what would this become? Then 2w of t becomes, this becomes 0, right, the first term. Right? And the second term becomes whatever it becomes. So it becomes L, so I can write the second term as L1 L2 minus m squared over L1 times I2 squared. So for this relationship, if you had this particular relationship between I1 and I2, this is the amount of energy that's delivered to this. But again, we know this is passive, right? What does that mean? And this is positive or 0. This is non-negative, right? So it means that this has to be positive or 0, right? So it means that L1, L2 must be greater than m squared. Or in other words, the mutual inductance has to be smaller than or equal the geometric mean of L1 and L2 for the element to remain passive. And of course, it needs to be greater than 0, but I mean, magnitude of it for this. So this is an important relationship, particularly this part of it, right? It means that you can't pick any arbitrary value of m, right? You can't just like pick some arbitrary value. So if your primary inductance is 2 Henries and your secondary inductance is 8 Henries, right? This cannot exceed 4 Henries, right? Square root of 2 times 8. So this is an important, otherwise your element is not passive anymore. Yes?
But isn't that only when the assumption is true?
Like, this assumption?
Yeah.
So no, what I'm saying is that this should be valid. This should be positive for any value of I1 and I2. So since it's valid for any value of I1 and I2, then it should be valid for this particular one as well. This particular one is chosen so that it creates a situation where this first term disappears, and that creates a constraint. It doesn't say necessarily it's a tight constraint. Well, actually it is, but this doesn't prove it. Meaning that your m can be square root of L1 and L2. And that's called a perfect transformer. In fact, we define, so this allows us to define another parameter that you will see. It's called coupling coefficient for a transformer, which is defined as m over square root of L1, L2. And you can see that this has to be smaller than or equal 1. Can't exceed. The coupling coefficient cannot exceed 1 because of this relationship. But this coupling coefficient captures a lot of essence of the transformer behavior in it. So if you have a k equal 1, so when k equals 1, we call it the perfect transformer. It means that m is the geometric mean of L1 and L2. And the perfect transformer has an interesting property because now a lot of things for it depend on really the ratio of L1 and L2, which is called the turn ratio. So n, which is defined as square root of L1 and L2, we call it the turn ratio, right? L2 over L1 really, because it's the secondary versus the primary. So L2 over L1, and this is called the turn ratio. And why is it the turn ratio? If you think about it, inductance is proportional to n squared, right? If you have n turns, a solenoid, the inductance is related to n squared. So what happens is that this basically gives you a ratio of the turns. It basically becomes the ratio of the turns if you have perfect coupling. And in this case, your relationships become pretty straightforward. The relationship you get are essentially going to be V1. So V1 and V2 are related through L1P I1 plus NI2. And V2 becomes essentially N times L1P times I1 plus NI2. Which basically means that this is, if you look at it, it's NV1. So it means that V2 over V1 becomes N. The ratio of the voltages for a perfect transformer is determined only by the turn ratio. If you have perfect coupling, the secondary voltage and primary voltage are only related through the ratio of the turn ratio, which is the square root of the ratio of the inductances. So this is a perfect transformer. Now, there's one more step you can take, which is called the ideal transformer. Now, if L1 and L2 both go to infinity, if L1 and L2 are pretty large, what happens is that you will see, if you look at this, for example, if you look at, you can write as like this, L1p equals I1 plus NI2. And if you let L1 and therefore L2, because the turn ratio is finite, go to infinity, this goes to 0, and which means that I2 over I1 becomes negative 1 over n. So this is what we call the ideal transformer. So there's a perfect transformer, where coupling coefficient is 1, right? And that is basically has this relationship between voltages. Now, if the inductors of the primary and secondary are large, then it becomes what we call a perfect transformer, ideal transformer, where there's this relationship between the voltages, currents as well. And what this does, it allows you to model it very simply, because then everything is determined by n. So in this case, for example, if you have a transformer, and if you have a resistor R here, you know the ratio of the currents, and you know the ratio of the voltages. So it does what we call an impedance transformation. So if it is, let's say, n to 1, right? The impedance you see across here, because the current is n times and voltage is kind of like scaled by 1 over n, the resistance you see across here is going to be n squared times R. So you can see that you can change the impedance up or down depending on how you use the transformer. You can make it up, go and down, go up and down. And all of this, so when you use this, and you can combine all of these things to produce a model that's a very useful model and generally true for transformers. You can actually take that T model that we produced before, and in the case of a general transformer, not ideal or perfect, you can actually model it in this form. So in general, a transformer can be modeled in the following way. And you can see it comes directly out of that T model that we produced and the ideal transformer model. So you can see that the entirety of the transformer, and so this is neither perfect nor, it doesn't have to be ideal or perfect. This is a general transformer. You can model a general transformer as a T model defined only with two parameters, K, which is the coupling coefficient, and L1, which is the inductance of the primary, and an ideal this is the ideal transformer with the turn ratio of 1 to n, where n is basically defined as the ratio of V1 and V2, which is basically the square root of L2 over L1. And K is m over square root of L1, L2. So if you start with a transformer with defined with L1, L2, and m, the primary inductance, secondary inductance, and a mutual inductance, you can model it always like this. And this doesn't even require the two lower terminals to have been connected with each other. So this is the model for any arbitrary transformer that's coming out of this discussion that we had. This is that T model, and then in conjunction with an ideal transformer that allows you to separate the secondary from the primary. All right. So that's kind of a very quick introduction to transformers and understanding it. Basically really comes out of the two-port model and thinking about the mutual coupling of the parameters.